sitting in brakes and long range and a long battery life. So looking at modulation methods, you've got the typical, amplitude modulation, the traditional old radio, then the FM, and then we moved in more, 20 years ago, we went to 2G and 3G and TDMA. We were dividing up the frequency into time slots. Old 3G or 2G phones used to, buzz when you put them near a car radio, because what you were hearing was the time slot. The radio would transmit 1 in 8. And then we went to CDMA, sort of 10, 4G is CDMA. So people are actually transmitting one on top of the other in the same spectrum, say a megabyte wide, but everybody is noise to each other. And so CDMA has got this wonderful technique of actually having it that everybody else is noise, and I can pick my signal out in amongst all the noise. And we talk about the noise floor. So if you went out outside with a radio receiver and just listened to just white radio noise, that's the noise floor. All these techniques before had to have 10 or 20 dB above the noise floor to actually just detect. CDMA will actually be under the noise floor, 10 dB under, and you can still pick your signal out. So LoRa is not using full CDMA as we know it, in terms of it's using a version of this, and the version or the concept behind LoRa is you end up with a cheap, or a very simple transmitter and a very simple receiver, and it's low cost. You're talking about a chip that's worth, maybe £5, £10. Whereas a CDMA, and you've seen in a 4G radio, would be quite expensive. But what you get is you get the benefits of CDMA. So you end up with not only a radio that can transmit low power, so you can serve power on the transmit side. On the receive side, it's highly sensitive, so you can transmit long distances. So we exploit that. But LoRa is a worldwide system, but every country seems to be different. So in Europe, it's the 868 megahertz band. In the US, it's 915. In Australia, it's a variant of that. In parts of Asia, it's 923. It's wherever there was some spare spectrum similar to the Wi-Fi bands, the same concept. It's free to use. You don't need to be licensed. You've got to stick within the rules for the use in that area. And one of the critical things is you can't keep transmitting on the same channel. You've actually got to change channels. So that in LoRa, the concept is there's a group of channels and you keep hopping from one to the other. So you minimise the interference to your neighbours. And there are other competitors to LoRa, and probably the most common one is Sigfox. And so Sigfox and LoRa, you see them, it's people rolling out these systems. The difference is that Sigfox seems to be, from what I can tell, is being picked up by people like the carriers who charge you on a fee-for-service basis, a bit like having a mobile data service from a mobile phone carrier. And so LoRa is been adopted by people who are doing it on a no-cost basis. It's a community-type service. There is a possibility that the 4G telephone network could be rolled out to a similar type concept. But what it seems to me is happening is that the technology is there, the capability is there, but the carriers can't quite work out how to make money out of it. Because what it will do is it'll scavenge their existing tariff structures. And so it may or may never be rolled out. So in terms of LoRa, there's a distinction between LoRa, which is two of these transmitter receivers talking to each other, point to point. And you can actually buy them quite cheap, put something like a Raspberry Pi behind each one, send them some AT commands, so it's just on a serial line. It'll be like AT, and then a command, and it'll just send the data, and the other unit will receive it, and it can answer back. And the two of them just quite happily transmit and send data over long lengths, long distances. Then on top of that is the concept called LoRaWAN, and this is where I'm working in this space, where there will be a gateway or a radio receiver, central, and a cluster of nodes around them within a sort of a 15-kilometre radius around that. And so the one I'm going to talk about is called the Things Network, which is based on a concept out of Amsterdam, started up about 2 or 3 years ago. But there are others. This is a community network, which you can even implement it now as your own private network. So what it consists of is the nodes on the other side, simple single battery transmitter sensor, quite small, compact, and that's what we'll put out in the vineyard. The gateway server is what I've been developing myself, based around a Pi, and everything on the right-hand side is being provided by the Things Network out of Amsterdam. And then you integrate it into any of these services. So in terms of, there's gateways everywhere. Not huge numbers, not full coverage, but in time that we'll see this system roll out. So where does the Pi fit in with this? So on the left-hand side, we've got the sensor, a radio link, and the gateway server. So it's really a combination of a LoRa radio unit and a Raspberry Pi, with this set of code typically written in C and compiled, and it's readily downloadable. Just a simple command, and you can load it onto a Pi. The radio unit and the Pi talk over SPI. There's a TCP or UDP connection back to the network server. So I just plug in an Ethernet port, so off my router at home, plug a cable into my gateway, and that's it. I don't need to change the router settings. I don't need to do no port forwarding. It's just a simple connection. So there's a gateway at the bottom and a Pi. Just one sitting on top, just like a hat. And that's the particular board I've bought out of China. And it consists of a number of chips in there. But primarily there's a single manufacturer of these chips worldwide. Semtech had actually developed LoRa and have commercialized the concept and have a monopoly on the chips. But they're wonderful. They're low cost, they're readily available, and there's people now taking those chips and integrating them into their own radio units. So we've basically got a couple of radio chips and a power supply, and this is the same size of the size of the Pi. There are gateways for indoors, and a large number of people have commercialised gateways for indoors, but you end up with a long antenna cable, 5 metres or something to go outside, and you get losses. And at 900 megahertz or 868, you can lose half the power in the cable very easily. So there are some outdoor gateways, and that's what I'm interested in, is how do I provide a simple outdoor gateway that I can actually put in a box, send it to someone, and they can install it, plug it in, say power over Ethernet, and away it goes. So there's my gateway at home. So I've packaged up all of that into a unit on top of a 7-metre pole. It sits a couple of metres above the roof line of the house, and I just feed it Ethernet with power over Ethernet injector, and it's simply a board that's arranged for 2 boards, the Pi and this is the Pi 3. So Andrew, when I was asking you about what are those pins on the 4 extra pins, it was me trying to work out how to do power over Ethernet and pull out of the.
I can see your 8 diodes and putting power out of the 4 pins.
Yes, except that on this board, the 4 pins, I was half a 0.05 out. I had to re-drill them.
Made exactly the same mistake on the board, didn't
Yeah. And then I learned all about the power over Ethernet. It's not 48 volts there permanently. Power over Ethernet puts in 2 volts because it wants to be backward compatible. And if it sees 25k ohm resistor which is down here, it then switches on 48 volts for a very short period of time. And if it sees the current go over 100 milliamps, it leaves it on. If it doesn't, it switches it back off. And so I had to cut and shut the board and actually put a MOSFET and a xenodiode and a couple of resistors there to switch on this board when the injector actually switched in in fact, it steps up. It doesn't go all the way to 48. It steps it up a bit, just enough to measure the current into that 25k resistor, and then does a step up. So I let the hardware go. I let all of that, what they call power over Ethernet signatures. But the thing I've come across is these boards are hot. They really run hot. So here's, I've got it sitting on a 10-degree day, 10-degree C night in this enclosure, and the chip, the Pi 3 chip is running at 40 C. And I'm going to run this at 45 degrees C outdoor temperature in the sun. So I'm going to get 20 or 30 degrees higher in the next side of the enclosure. So I'm already up at like 65 enclosure temperature. And I've got the Pi can only go to 80. And the LoRa chip can only go about the same. And it's even hotter. So here's the LoRa chip. It's running 69. So it's 40 odd degrees, 45 degrees hotter than ambient. This is not going to work. So I start modeling, doing thermal modeling of the chip. So what I'm looking at there, if you haven't done thermal modeling before, I'm considering, instead of voltage and currents and resistive drops, I'm thinking about watts of heat, temperature difference, and I can actually go back and predict what my temperature is. So I've got the heat coming in from the radio chip. I've got the heat coming in from the Pi. I've got the heat coming in here from the sun sitting on the enclosure. And what I need to do, I need to reduce the heat in the Pi. So I need to move away from the Pi 3 because it generates a lot, it chews up a lot of power, generates a lot of heat. And I've got to do something with this particular LoRa chip I've got. So off I go. I think I'll leave the Pi community and I find these chips. They look really attractive, except the first one, the SPI port doesn't work. It will transmit or it will receive, but not simultaneously. Minor problem. So we go to the second one. That looks even better, except the manufacturer decides to pull it off the market because in the future they're going to do an upgrade. Now I've got a supply problem. I've got a problem of I can't rely on this being available. It's come back on the market again, but I'm too nervous. And I come to this last one and I find out it's got the same hardware problem that the first one's got. So I've spent about 3 or 4 months going around these chips only to realise I've got to come back. So I'm back. And so now I'm back with a Pi 0 and a much smaller LoRa radio chip. So this has effectively got 8 receivers. Well, in fact, it's got 10 receivers and a transmitter in that one little board.
Why multiple receivers?
I'm sorry, because one of the things about LoRa is it wants to keep changing channels. Yeah. So my central base station has got to listen simultaneously on 8 channels. So the concept of LoRa WAN is you listen on 8 channels simultaneously, right. And you build LoRa WAN in blocks of 8. So you've got to go, and in Australia we've got 64 channels, so I can go in blocks. So the Things network has like in Australia has said we're going to start in block 2. So we're in channels 8 to 15, because that's by convention, that's where we're all going to be, because otherwise you're starting transmitting around and there's no receiver, so you've got to hop and keep hopping and hopping until you get an answer back. Well, that's wasting power. So why everybody sticks to the same convention. Now once you've actually made a connection, the gateway will tell the node what the frequency block is. So as long as you can actually connect the first time around, you conserve energy. And you can then train the node what you know, is this an 8-channel, 16-channel, you know, 64-channel network? So it's now a convention that these radio units are built in blocks of 8, and all I do is I just stack these up. The simplest thing is to put 2 antennas. If I wanted a 16-channel system, I just put 2 antennas on. I wouldn't go trying to combine them into one antenna. It's just not worth it. These are so simple to do. So where I'm back is I'm now developing a board around this, and there are lots of other people doing exactly the same thing. What I'm looking for is something that will sit in at 45 degrees C, and be very simple to deploy. A lot of them you need to be local. You've got to do sorts of things. So things like using resin and Docker is attractive. This is about to go through another revision in terms of version 3 of the LoRa WAN or the Things network, and that may all get superseded and maybe incorporated into is part of the infrastructure. So the Pi gives me flexibility. I can write my own code. I can add my own extras. I can put it through Docker, and that's why one reason I'm back in using the Pi. Just all the extra things I can put on. Just quickly as a diversion, because when you build these things, you actually put an antenna. At the end of the day, you've got to put an antenna on it. And you see a lot of people building these things, and they've either got a software background or a hardware background, but they have not a radio background. And the success of this comes from a good antenna. And there's lots of rubbish around in terms of, people advertise a high-performance antenna, and you find actually it's very poor. You actually got to go out and test or evaluate your own antennas. So one method of doing it is it's called VSWR. So you're looking at the amount of power you're putting into the antenna from the connection, from the connector, and you want to see how much is coming back at you. Because if you're not getting 100%, if 100% of what you're sending is not being radiated, it's being lost. And so VSWR is a measure of how much is coming back. So there's a simple graph of VSWR versus frequency. So I picked the center frequency, say 868 for Europe or 915 for Australia. And this is telling me that this antenna would be tuned for that frequency, but it's not tuned for adjacent frequencies. And so there's a little device. I said this is another tool for Richard to buy. You can always tempt him with another. And so these are literally couple of £100, about £100, I would imagine. Traditionally, I was looking at, I've traditionally used a $20,000 or £10,000 radio test set for this sort of thing, and that's a cheap test set. And these things are just dedicated to this function. These things are brilliant, and when you put them up against a high performance test set, they actually do work. They're not, they really are good. So you tune up you can see here, out of focus, but we've got 926 megahertz, 906 on the other side. It's about 915 or 916 at the marker. So I actually build an antenna and I can actually tune it and I can see it. I can actually cut the antenna, just keep lopping a bit off the top until I get the dip. And I look in here and I'm getting a VSWR 1.2 or thereabouts. That's good. Now I can look up a table and convert VSWR to actually percentage reverse power that's coming back, and it's in the order of 0.25% or half 1%. That's okay. And then we then look at, okay, well, I've got a test set. What sort of antenna I'm going to make? And so what you're looking for here is the thing about an antenna is you want it to radiate out horizontally. You really don't care how much power is sent vertically up or vertically down, because there's no nodes sitting above you or directly below. They're generally out in the horizon. So we draw this sort of graph, and you can do quite a sophisticated modelling these days. So a little antenna like this, and it's literally a connector, some bits of copper wire, maybe 100 millimeters long, thereabouts. And in fact, there's plenty of these information about on the Things Network forums. You can make that in minutes. Just solder the lugs, solder a bit of wire into a lug, screw them together, and there's an antenna. And they are really a high-performance antenna. And a number of these more expensive, higher gain antennas actually don't work as well as this. They can have claims of much higher gain in terms of actually putting even more power out horizontally and less power in the vertical, but these will outperform them.
Is this two different antennas, or?
No, the reason for this is when you have the radials, and that sort of replicates the traditional whip antenna on top of a car, you put an antenna in the middle of the roof. The impedance of the cable feeding that is 50 ohms, and a LoRa system going at 50. That's got an impedance of about 37 ohms. By bending them down at 45 degrees, it brings the impedance of this network up to 50, and you get a better match.
Which way is it pointing?
Horizontal. So it's actually radiating the equal amount in all directions horizontally. What it's done is taken power that would have. So if you think about an isotropic radio, it's like a light globe. It's radiating power in all directions equally. Yes. So this is actually scavenging power from the vertical and compressing it down and radiating it horizontal. But it's uniform in all directions.
What is the main pattern and for you?
That.
Okay.
So
you're losing quite a bit of power at various elevations.
So if you put this on a hilltop, all of that's wasted. 50% of your power is wasted. What you'd like to do is try and bend this down a bit.
Just because it's pointing in the wrong direction.
Yeah, it's better than isotropic.
But in elevation as well, you've got power.
Yeah. So what you'd like to do is scavenge some of that power on that and put more out horizontally. And that's what a higher gain antenna claims to do. But there's compromise.
Otherwise, just put a mirror behind it.
You could, but then it's directional one direction. So one of the things I'm interested in is I've got nodes in all directions. So I need it to be unidirectional. Well, sorry, I want it to be omnidirectional in my application. If you knew all your nodes in one direction, you could then scavenge the power from behind you, as you say, put a reflector in, and there's a technique called a Yagi antenna, where the traditional TV antennas like that. There's extra elements put in front and behind of the radiating the element, and it brings power from the back and focuses it to the front. I can bore you stiff with another 1-hour presentation on that too. But these work well. So there's a higher gain antenna, simple stick, with a fiberglass radome on top. And so I couldn't help myself, could I? I got the Dremel out and cut the thing open. And so this is claimed to be a 6 dBi, whereas the previous one's 2 dBi antenna. And what it is actually, it's 3 dipoles stacked vertically, one above the other. They're quite sophisticated to make. So I've had other intentions of doing it another way. But you need to do a little bit of work in antennas to make LoRa work. You need to understand how they work, because all the work you can do in a transmitter and the code and all that can be completely destroyed by not having this bit right. And there's a golden rule in this, is that people say, oh, I can get you a 10 dBi antenna, or I can get 12 and all that. Don't worry about that. Just get a bit of height. Antenna height trumps everything. You'll get more effect by putting it up another few meters. Get it like I've got at home, I've got it 2 or 3 meters above the top of the roof line. I'm not sitting down amongst the clutter, the electrical clutter. I've got a bit of elevation, and that outperforms anything. So mine will go at least 30 kilometres. I can go way beyond the 15 kilometre guaranteed range just by getting it 2 or 3 metres above the roof line. So what's next? Well, I'm going back in a few weeks' time. I'm going to be building gateways. I've got 20 or 30 to build. Half a dozen gateways to build, 20 or 30 remote sensors to put out. But I think we have to test these gateways, don't I? So I'll get into it. I'm seriously looking at the moment at actually programming a drone to actually fly a known course, fly to a point, do a transmission. I can record what the signal strength is, fly to the next one, do a transmission. So all I'm going to do is take a drone with a camera. Instead of it firing a camera to take a snapshot, we'll just get it to transmit get the LoRa, the small lightweight LoRa node will be sitting on the back of the drone, just to fire it off and give it a transmit signal, and come back and
can the sensors talk to each other in a mesh, or do they have to talk direct to the gateway?
The way that the LoRaWAN works is to a gateway, but I can easily put things like a GPS receiver on them, and either timestamp it as well as position stamp them. But no, in this particular LoRaWAN concept, it's a node to a gateway. What you do behind the scenes after that, mesh it up, daisy chain them, that's your choice.
You were saying that LoRa kind of depends on having background noise, and out in the middle of the desert or where it's very, very quiet, there is none.
They will work even better.
They work even better.
It's not you need noise, it will work in the noise. And because of that, you can get extended range, or you drop the transmit power. And one of the things you always remember, if you have a high power transmitter at one end and a low power transmitter at the other, one will hear the other, but not reverse. And LoRa relies on you send a signal in and then you acknowledge it back. So rather than cranking up the power on the gateway and turning the power down on the node, you need to have them balanced so they can hear each other. And you do that either by raising the antenna height, increasing the gain on either end antenna, or like in the desert, you put it in a low noise environment and you exploit that. And most of mine will be kilometres away from anything, so I'll be exploiting that. And some reference, I'll publish this on the site, so there's a whole stack of references you can have a look at. And effectively, the purpose of this is to say, I've been playing with this for a while. If you get into it yourself, make contact, and I'll point you in the right direction. Cool. Yeah, that's it. The total value.
Total budget of money.
Index
cost.
How many? You can build a gateway for say £200.
£200 per gateway.
Yeah, and you could build a node for £20 or £30, maybe even less. It can be real low cost, particularly if you do it yourself.
Oh, yeah. I need to hire the kind of company like you, or hire.
No. The Things Network is a real self-help group.
But the constructing gateway and that.
The beauty of the gateways is you can put your own node in. If there's someone near you with a gateway, one of the things, this is a shared network. I can actually bring a node with me from Australia, change the frequency, and I'll hook up to anybody to a gateway here in the UK. I don't have to own the gateway. As long as you've got a node and you're near someone else's gateway, it's a shared resource. And that's what that map of the world is. If you can find a gateway nearby, you use their gateway.
And the gateway allows you the connectivity into other internet-based services?
Absolutely.
Okay.
Do you find that the UK government is getting behind TPN or LoRa? Because a lot of the discussion I hear is around 5G, the excitement from say, because it's TPN is expanding rapidly, but you do wonder if the government or if NADK were behind LoRa, how much faster
Yeah, because I come from Australia, but I was involved years ago in spectrum auctions. And I think they're two separate things. And the reason you have a lot of conversation about spectrum auctions is it's a lot of money behind it. But they're two separate markets. 5G is all about large volumes, high data rates. LoRa is about the opposite. So I see them as being complementary, not competing. One of the things you would quite often do with a gateway is using a 4G or 5G backhaul. If I've got a gateway put in the middle of a agricultural environment, how do I get back? I don't have an Ethernet cable, so I'll put in a 4G or even a satellite. And in fact, you'll see me some people might have seen actually on an advert for a satellite system running, and basically they're putting a ground station in to a satellite, to a low Earth orbiting satellite, and it's LoRa to their gateway.
What about solar power? Instead of relying on a battery, you've got
And so that my gateway will be solar. You can either power it with an injector, or you can put a solar panel on it.
But your transmitting stations, can they also be powered by?
They can, yeah.
And then you could perhaps transfer more.
You could, but what I'm interested in is something as simple as a simple low-cost node with a single sensor that I put a single battery in. It'll last a couple of years, and I don't need the complexity of. As soon as I put a solar panel on it, I've got more installation issues. I've got penetrations into a cabinet. I've been able to water seal it, and it scales up. So this is about simple, low cost, low complexity.
What do nodes actually look like? Is it very similar to your gateway then?
They will actually be in a small plastic box, probably 100 millimeters by 50 by 50.
You don't need a huge antenna.
No, in fact, I'll put the antenna inside the plastic box. I don't want a penetration coming out. It's another source of getting water into the thing. There are plenty of stick-on, literally antennas with adhesive on one side to peel it off and stick it on the inside of the lid and connect it up. And they're really low cost. So they're simply a flexible printed circuit board, an antenna made out of a flexible PCB.
I'm thinking very, very shiny spheres that don't get any heat and keep the ambient temperature inside very low or underground, but evidently not. That's not a good idea.
And so people are talking about using LoRa on water meters for signaling back, for electricity meters, for gas meters. There's a very simple method where you go into someone's property and the water company or the power company says, I want something simple, compact, and I don't have all the complexity of connected up, and they put a solar panel on this customer's house. And it's that sort of application you see time and time again LoRa being talked about.
Military applications.
And
MEMNETs, MEMS are distributed out in desert environments.
Yeah.
For detecting troop movements using similar types of technology.
Yeah. And I would
It's
imagine.
LoRa or not, but it's low frequency, long lasting.
Yeah, it's the same principle. You want something simple and quick to deploy, and it's not complex.
And they're small.
Yeah, and you wouldn't even know that.
They sprinkle a mile into the desert.
And that's what LoRa does. It's got its place.
The over the horizon. So this is operating at 900
It's absolute line of sight. You won't go over the horizon.
So the horizon's only like 5 kilometers away for a person standing up. How are you getting 30 kilometers?
It depends where you are. So if I get a bit of elevation on the gateway, if I can get up 7 or 8, 10 meters, I can get. And particularly in my application, I'll be putting the nodes up about 2 to 3 meters in the air, and I can get that sort of range.
Quiet environment.
Yeah. Just build.
Yeah, similar to your application, if the agriculture, the farmer wants to hire someone like you, How much total cost to get it?
Oh, very expensive.
Yeah, I know, yeah. So the,
I'm doing this as a part of a research project. It's literally a R&D project.
Yeah.
Um,
how year, 1 year, how
oh, so I'm doing this part time. It's a sort of self-interest thing at the moment.
Right.
Um,
long will the duration of the project?
oh, this will be a 1 year project,
1 year.
end to end. Yeah.
I have a friend in the UK doing something very, very similar in Bedford. Private sort of experimenting. I wanted you to meet him, please.
Yeah, so it's interesting stuff. I mean, and that's why I'm sort of presenting this. It's quite interesting to get into, and you use a Pi.
I was just curious, your original prototype, you're using power over Ethernet with the Raspberry Pi 3.
Yeah.
Then you switched to a Pi 0, which doesn't have an Ethernet port in it.
Yeah.
Did that created a complexity dealing with tapping into power over Ethernet or the setup to, or did you continue to use Ethernet as a source of power, or did you switch to something else?
No, I'm putting my own SPI to Ethernet chip in and my own magnetics, and I'll build a complete power over Ethernet and a full Ethernet connector on a Pi 0. And that's one reason I was looking at these other chips, because some of them actually have the drivers straight out to the Ethernet magnetics, and that was the real attractor with them. But they all came with these other, all had their own individual problems. And I must say that the lack of support that the Pi community and what it's got is quite it's quite outstanding in terms of the amount of published information, people who are there who help you. In these other areas, as soon as you get outside, you think, well, it can't be that hard. You step out and you suddenly learn that there's a lot of shared resource in the Raspberry Pi community you just don't get elsewhere. That's one of the reason I sort of came back.
Keep that in mind, everyone. Well, thanks very much.
Yeah. Anyway.
I've got Ruben up next. Doing part 2 of his Linux drivers.